So I've just pulled out a slide in the middle of the PowerPoint presentation on ordinal logistic regression. And so what's on this slide? What's on this slide? Well, what I put on this slide is the formula for the ordinal logistic regression model that considered the Acinetobacter study, where the outcome variable was length of stay in the hospital, treated as an ordinal variable in 3 categories, okay? And it's an ordinal logistic regression model, and it's a certain type. There are several different kinds of ordinal logistic regression models, and this type is called the proportional odds model. It's also called the cumulative logit model, but it's called, either one are 2 equivalent ways of saying what it is. And it's a model that satisfies something called the proportional odds assumption, which I just want to quickly kind of review what that means again. And I mentioned something about what you have to do to check the proportional hazard assumption. So what do you have to do? What's ideally what you want to do to check the proportional hazard assumption? There is something called the score test for that, okay? The score test for checking the proportional hazard assumption. And the null hypothesis for that test, it's a chi-square test, chi-square statistic. The null hypothesis for that test is that the proportional odds model that you're specifying, like this one, is okay, it's suitable. It satisfies the proportional odds assumption. You can use this model. And the alternative hypothesis is that this model is not appropriate, okay? So what you do is you run, if you're using proc logistic, which does this, the proportional odds model, you put in your programming statements, which we've shown you already, and you get your output, and within the output you're going to get that chi-square statistic for the model that you're running that's going to tell you whether the proportional odds assumption is satisfied or not for the model that you're running. And if it's satisfied, then you can use the model. If it's not, then you have to decide what to do. And if it's not, there are some alternatives, and one of the alternatives is do some of the other approaches, but unfortunately, the other approaches aren't built into SAS, Logistic, or any other program that's packaged in SAS, so you're going to have to, if it's in your own research or your own thesis, you're going to have to look up the appropriate papers that will, and computer programs that will let you do these other things. Alternatively, if the proportional odds assumption is not satisfied, you could use polynomous logistic regression to come up with another way to do the analysis. But you might be losing something rather than doing a different form of ordinal logistic regression if you do polynomous, because you're not taking into account the ordinality, and you might not be getting as strong or as powerful a test or as accurate an estimate of the odds ratio or describe whatever you're trying to evaluate when you're fitting this model. So anyhow, this was the model that we considered here, and the exposure variable was AC status, and there were 3 sets of variables, Apache, Charleston, and age, categorized into 7 groups. That were in the model, and that when you ran this model, you wound up getting, I didn't put it on, that's the model. When you ran the model, you wound up getting this output, okay? And you notice that in the output, each of the variables that are in the model are listed only once. Well, there are 7 variables listed for the matching variable. This is not age. This is the matching variable. The time and the time somebody was in the hospital prior to the infection occurring. That was the 8 categories, and there's one variable mentioned for each of these different dummy variables. And the AC status variable and Apache and Charleston are all there. You don't see two estimates for each one of these variables, only one. Okay, although you do see 2 intercepts, because the model, if you go back to what the model looks like, there are two intercept terms when you're doing ordinal logistic regression. And so as a result, you will get estimates of each of these intercept terms, and one of them is, because of the nature of the model and the characteristics of the model, is always going to be larger than the other, okay, for whatever that's worth. But you're not that interested in the intercept, you're interested in the effect of exposure. And that variable in this case is AC status, and the effect of exposure controlling for the other variables in this model, which is a no interaction model, is described by the estimate of that the coefficient of that variable, and whatever the other information you want to use to decide whether that the odds ratio that corresponds to that is significant or not, and to get a confidence interval around it. And so from this output, you can get an appropriate odds ratio, you can test hypothesis and get a confidence interval. In fact, on the next slide, I actually have what the odds ratio estimates are that correspond to each of the variables, but the only one of interest is the 1.987, because that's e to the beta for the exposure variable that controls for the other variables, okay? And there's a confidence interval around that, which includes the null value, so it's not significant at the 5% level. And it's sort of fairly wide, but that's not as important as saying that it's maybe not significant, even though the odds ratio is not close to 1. It's almost 2. Still not significant. Now, one question that came up, continues to come up, and some of you came up after class, was, well, what does this odds ratio mean? What does the 1.987 mean? How does it differ from what you get out of when you're doing polynomous logistic regression? What's the difference here? Okay, because you're only getting one odds ratio, right, when you're doing ordinal logistic regression that compares exposed with unexposed, in this case, susceptible versus resistant patients. Okay, so what's the difference here? Well, again, when you're doing polynomous logistic regression, you get as many odds ratios that compare each of the categories of the outcome variable with a referent group. So if you have 3 categories, you get 2 odds ratios. If you have 5 categories, you get 4 odds ratios, each one of them comparing one of the categories to the referent group. But when you're doing ordinal logistic regression, you just get 1 odds ratio. So what does that mean? What does that 1 odds ratio mean? Okay. Well, there's a number of ways to say that, what it means, but it's a one way to say it, it's just sort of an overall summary measure of the effect of exposure, considering the fact that you've got this data and you've got an ordinal outcome, and you're trying to come up with an overall assessment of what the effect of exposure is. So that's one way to say it. Another way to say it is, if you remember when I originally showed you the crude data and how I split up a 3x2 table into 2 2x2 tables, and then I showed you with each of the 2x2 tables you can compute an odds ratio when I looked at that 3x2 table. And each of those odds ratios, if the proportional odds is satisfied, at least for the crude data, they should be about the same, approximately the same. And that's actually what the proportional odds assumption is testing, although when you've got more variables in the model, the proportional odds is testing the model, whether the whole model satisfies the proportion, not just the crude data. Okay, so now when we looked at those odds ratios, and I won't go back to the slide, but I had 2 odds ratios and they were approximately the same. So you might say, and this is essentially what happens, is both of those odds ratios were around 2. If you remember, actually that was what they were, around 2 for the hypothetical data, and they were around 2 even for the, but one of them was a little above 2 and one was a little below 2. So I think, actually I don't remember exactly what it was, but in any case, you can argue or you can reason that this 1.987 is sort of like a weighted average of all the different odds ratios that you get when you consider how you cut up the total table into subsets of tables, of 2x2 tables that consider everything that you're controlling for. So it's a weighted average. It's a summary measure. It's a single measure. And it says no matter how you split the things in terms of category 2 versus 0 and 1, or category 1 and 2 versus 0, you're basically getting the same odds ratio. And what that essentially means is the different estimates that you might get, depending on how you split things up, are both estimating, they're all estimating the same thing. So what you're getting out of the model and out of the output is an average value for that. That's essentially what it means. I don't know whether I've explained it well enough, but that's what you're getting out of ordinal logistic regression. If you want to get different odds ratios to compare things to a reference group, then you shouldn't do ordinal logistic regression. Except that if you do polynomous in order to get that, and your outcome is ordinal, you're not necessarily getting as much power in the analysis in terms of getting a reasonable result about the exposure-disease relationship. So that's what what this is sort of about as far as what the odds ratio means. I mean, that's one key question. Another issue was, let's go back to this. What is the proportional odds assumption? And in order to get that, I just want to make sure you remember seeing that there are two ways you can write the proportional odds model. One way is a probability statement, and it's a probability statement that doesn't talk about the outcome equal to something. It's an outcome saying y is equal to greater than one of a number of values it could take on, and it's in the form of the similar form to what the logistic model, binary logistic model, looks like, except it's no longer 1 over 1 plus e to the minus with a single alpha. You have several alphas, but depending upon what the g is, what the value of g is. But an alternative way to write the model, an equivalent way, if you just take the log odds, you'll wind up getting the log odds is equal to the linear part of this model. The log odds is so that's another way to write the model. Why is this an odds? Why is this the log of an odds? Because this is the probability that y is greater than g divided by 1 minus that probability is the probability that y is less than g. So this is an odds. And the algebra or the mathematics of this thing will show you that the log odds is this linear function. And that also means that the odds has to be e to that function. Okay? So if you want to get an odds ratio, you take the odds for one person and you divide it by the odds for another person. One person might be called person X star and the other person might be called person X. So if you wanted to get the odds ratio, what you would do is you would take the odds for person X star divided by the odds for person X. And I showed you this last time. That would be the numerator. That would be the denominator. The only difference is that we're talking about two different people who have two different specifications of the predictor values. The predictor values are called x's. And so when you do the algebra here, you notice that alpha sub g cancels out of the numerator and denominator, and you wind up getting an expression for the odds ratio that doesn't involve g. So the odds ratio, when you're using the proportional odds model, doesn't involve g. It's constant. It only depends upon the regression coefficients, which don't depend upon g. So, and another way of saying that, if you do a little algebra with this, is that since the ratio of the odds for these two different people is equal to a value that doesn't depend upon g, then the odds for one person is equal to that value times the odds for the other person, or like A is equal to a constant times B. If A over B is equal to C, then A is equal to C times B. And that's essentially saying that you can get one odds from another by multiplying it by some number that doesn't depend upon G. That number is often referred to as a proportionality constant. And that's why it's called the proportional odds model, because if you use this model, this is a truism that results from the model. So that's why it's called that. Okay. Now, just as a final review, before I'm still trying to do some final review of this thing, I'm going to consider a more general situation. Let's look at this screen. I'm skipping until right near the end of this slideshow. Let's look at this screen. See if you can find that. Right near the end, right? You got it? Okay, so what have I done here on this slide? Well, on the top it says an example of a polynomous logistic regression model. Is this an example of a polynomous? How do you know it's polynomous logistic regression? Because the way I've written the model log P of y equal to g given x divided by y equal to 0 given x. And you notice there's no greater than or equal to sign. So I'm comparing the gth category with the 0th category. So I'm comparing one category with a reference group. And as soon as you see that, you should tell yourself this is a polynomous logistic regression model. And here's what the model would look like if you had a single exposure, keeping it simply, not several exposures. You have a single exposure, and you had three variables you wanted to control for, and you put them in the model at just as themselves. So the V variables in the model are the same variables as the C's, and you're also putting them in the model as products with E. So the W variables are the C's also. So this is a polynomous logistic regression model involving an exposure-disease relationship controlling for three C's and allowing for interaction. Correct? That's what this model is. Can you see that? Just trying to make sure you can see that. And for this model, the formula for the odds ratio, since there's interaction, involves the coefficients of all the variables that involve E. And one of them is beta sub G, and the other is the deltas, which are in there as products with E times C. So it's the usual formula for an interaction odds ratio. It's e to the beta plus the sum of the delta W's. That's what this formula is saying. And that would be, if you fit this model, this is what you'd get for the odds ratio. You'd crank it into using the G logit, link equal G logit, when you're using SAS, and you'd wind up getting these estimates, and it would be in your output. And if you want to test for whether if you wanted to test for interaction in this model, the null hypothesis for the test for interaction is that all these deltas are equal to 0. How many deltas are there? How many are there? Are there 3? Well, there's 6. There's 3 for, there's 3 deltas, but then there's 2 G's. So there's 6 deltas. So if there's no interaction, all 6 deltas are equal to 0. So in order to do that, what you would do is you would fit this model, which has basically there's 2 parts to this model. There's two versions of this model, depending on whether G is 1 or 2, and you'd wind up getting the full and the reduced. So what's the reduced model? I'm just reviewing everything we've done. What's the reduced model under this null hypothesis? It's the no interaction model. It doesn't have these product terms in here. And so what you do to do this test, this so-called chunk test, is you get the likelihood ratio statistic, which subtracts the reduced log likelihood statistic, the full log from the reduced one, and it would be a chi-square with 6 degrees of freedom. Why 6 degrees of freedom? Because you're testing 6 deltas or 6 parameters that you're setting equal to 0. So that's how you do that test. And if it turns out the test was not significant, then the reduced model, if you decided you went backwards and you tested, you went through the modeling strategy we talked about and decided there was no interaction when you did the chunk test and went backward, then the reduced model would look like this. It doesn't have any product terms in there. And in this reduced model, the formula for the odds ratio is just e to the beta, but there are several betas. There's 2 betas in this case, if G is equal to, if you've got three categories, and so you've got 2 G's to deal with. So that's how, this is sort of a review or a summary of what you would get out of polynomous logistic regression. Okay? You follow that? Okay. Now, look at the next slide. This is what the model would look like for the similar situation, but if your outcome was an ordered outcome. So this would be the ordinal logistic regression situation if you had 3 categories of the outcome and they were ordered. Okay? And this is what the proportional odds ordinal model would look like, because now you're writing the model as, well, writing the model as the log odds. And the log odds is the log of P of y greater than or equal to G given X divided by P of y less than G given X. And this would be the expression for it if you were going to allow to look at the effective exposure, controlling for the C's as potential confounders and controlling for the C's as potential effect modifiers. This would be what the proportional odds model would look like, which you'd want to check to see if it satisfied the proportional hazards, the proportional odds assumption before you went any further. But for this model, the formula for the odds ratio is this expression, e to the beta plus the sum delta j cj. That's the formula. Okay. Now you notice you're going to get one number here once you specify certain values for C. In other words, you're getting, there's no G in this formula because the G is in the alphas. The G is not within any of these variables. So that's the formula for the odds ratio. And if you wanted a test where there's interaction, the test, or at least the chunk test for interaction, would be that the deltas that reflect the interaction terms, the E times C terms, those deltas would be equal to 0. How many deltas are there in this case? It's not 6, it's 3. So the null hypothesis is that the 3 deltas, not the 6 deltas, because you're dealing with a different model, that these 3 deltas are equal to 0. So again, you do a likelihood ratio test fitting the full and the reduced model. This is the reduced model, doesn't have the product terms. And that would be a chi-square, when you get the likelihood ratios, to the chi-square with 3 degrees of freedom, because you're setting 3 deltas equal to 0. If it turns out you decided that you don't need these interaction terms, then the reduced model would give you an odds ratio that's simply e to the beta. And it would just give you a single number for what the effective exposure is, controlling for these other variables. And again, you'd have to think of this single number as some average of the different values that you'd get for an odds ratio depending on how you cut the pie, in some sense, depending on how you cut a 3 by 2 table. Okay? But that's what an ordinal logistic regression. So those are the two models. That's how they compare. Question? Yes, Michael. Right?
Yes.
Okay.
So, in talking about the interpretation of the odds ratio for the ordinal logistic regression.
Yes.
So when we first learned about modeling, we talked about like a 1-unit increase when interpreting the odds ratios. But then for nominal, we went away from that because a 1-unit increase.
Well, the exposure is, in this case, both the exposure and the outcome are categorical, right? So if the exposure is categorical, then we're not worrying about a 1-unit increase. If the exposure variable was systolic blood pressure, then then that's when you start thinking about the 1-unit increase. Okay, I think that's what you're saying. With systolic blood pressure, e to the beta in a model that's a no interaction model represents the effect of a 1-unit increase, a 1-unit difference in the value of the exposure variable. And if that variable was like systolic blood pressure, that wouldn't be very meaningful. You might want to get an odds ratio that considers a 20-unit or a 40-unit difference between systolic blood pressures, because that's the difference between healthy and not so healthy. Okay, is that what you meant? But you haven't asked your question yet.
Yeah, right. Well, so I mean, I guess even thinking about dichotomous, right? Like the difference between 0 and 1 was still like a 1-unit increase. So I guess the question of
there's only a 1-unit increase. You're only talking about the difference between, what if you go from exposed to unexposed? That's the 1-unit increase. So it really doesn't. You don't have to worry about that because you're dealing with a categorical or a binary exposure variable. So you don't have to. You have to worry about it if it turns out the variable is something different, either a continuous variable or a variable that's. I'm talking about an exposure variable that's either continuous or could be ordinal. You could have the E variable could be 1, 2, 3, 4, 5. Then you have to be talking about a 1-unit change in the E variable as you're going from 1 to 2 to 3 to 4 to 5. And you're going to have to talk about that because you're no longer dealing with a binary E variable, regardless of the D variable. And in any case, the D variable, whether you're dealing with polynomous or ordinal, the D variable is categorical. You're not dealing with a continuous outcome here. You either have two categorical values, or you have more than two if you're dealing with either polynomous or ordinal. Okay? And we can talk about this some more. Any other questions? I don't. Oh, okay. Back there. Is that Sadaf? How did I get that? I can't even see. I'm having cataract surgery on Monday, and somehow I still managed to, so. Will I be here on Tuesday? I hope I will be, but, yeah.
So if you go from 0 to 1 and 1 to 2, different that situation,
Yes.
would the ORs theoretically change or not? That's what I'm, like, the interpretation.
Well, again, you got to think about what you're doing. What you're doing is you're not comparing the odds ratio going from 0 to 1 or from 1 to 2. You're comparing the odds ratio going from comparing 0 to 1 and 2. So you're not comparing 0 to 1 or 1 to 2. You're comparing two ways to cut those three categories into two groups. 0 versus 1 and 2, or 0 and 1 versus 2, but not 0 and 2 versus 1, because that doesn't use the ordering. Okay? So you're not going from one to the other. In fact, if the proportional odds assumption is not satisfied, there is an alternative procedure that you have to find the program to do it. It's called the adjacent, something like that, the adjacent odds model, and which allows you to go from one to the next one for adjacent ones rather than cut it how you cut the pie. Talks about something about adjacent ones where you could look at, but that's a different model. Okay. Anything else? Okay, so the only other thing I wanted to make sure I showed you was this next slide here. Let's see. I think this is the last slide because, yes, it's the last slide. Look at this slide. Now, the model that I'm putting on this slide, this is the last slide in this thing. This is, again, the same ordinal logistic regression model that I showed you just before on the previous slide. Okay. Now, what I'm now writing is some expressions not for the odds ratio, but for the odds. Remember, this is the log odds. The model is giving you something about the odds or the log odds. It's giving you an expression for the log odds. If you want to get an odds ratio, you have to take an odds for one person and divide it by the odds for another person. But if you're talking about the odds, you're only talking about one person. So if you're talking about the odds for a certain person and you're saying, well, what's the odds that the outcome is going to be greater than or equal to 1, this would be the formula for it if this was your model. What have I done from this model to get this formula? What have I done? How does this differ from that? I plugged in 1 because I'm talking about y equal to greater than 1. That's the g value I'm talking about. Okay? And if I'm talking about the odds for y greater than or equal to 2, I take this formula, I plug in 2 for g because I'm talking about the other value that you can only be greater than or equal to 1 and greater than or equal to 2 if you have 3 observations and it's 0, 1, 2. Everything's greater than or equal to 0. That probability that y is greater than or equal to 0 is 1. Okay? Because 0, 1, 1, or 2. But anyhow, if you look at these two expressions for the odds, well, one of these odds is not equal to the other odds. Why is that? Because this has alpha 1 in the formula, and this has alpha 2 in the formula, and what do you know about this model? Alpha 1 is greater than alpha 2, so you know that this odds has got to be greater than this odds. So the odds, when you're dealing with a proportional, the odds do differ. The odds ratios don't differ, but the odds differ, depending upon which odds you're talking about. Okay, so I don't know. That's something. So one could ask on an exam, for example, something about, well, what's the odds look like? And if you wanted to compare two people, and when you're talking about two different odds, what would they look like, and how would they compare? Well, in this case, this odds has got to be greater than this odds because this odds involves alpha 1, this involves alpha 2, and alpha 1 is greater than alpha 2 because that's what the model says. That's what's assumed in the model. Okay. Now, with that, I'm going to, unless you have any questions, I'm ready to go on to collinearity. Can I do that? Okay. Well, I guess I will. Okay. So, I cut this out, and now I talk about collinearity. It's an interesting topic, although what's interesting? I don't know what's interesting. Is this interesting? Well, you know, how many of you really wanted to be in this class other than the fact that it was required, right? Well, some people wanted to be in this class because they thought maybe they'd learn something in this class, you know, and other people may not. They required. In fact, I won't get into this in any big way, but the Department of Epidemiology has been doing a curriculum review. And they formed a committee that involves a bunch of people that don't involve the people who are teaching these courses, teaching the methods courses. And they've decided, or at least they've recommended, that this course no longer be required. So next year, if their conclusions hold, whoever's taking this course because it's required won't have to take it. But of course, you're taking it now because it's required now. So, but I'm not very happy with that. But as you can imagine. But anyhow, that's another story. Okay, that's why I'm not going to get into that. So let's talk about collinearity. But I'm not too happy about it. But okay, so now this is the slideshow about collinearity, and as you saw, I sent you all an email. I modified it again a little bit today because I wanted to make it clearer. Okay, and I sent you an attachment so you could have that in front of you if you wanted to. But I kept the other one in there so you can have that in front of you. And I didn't make hardly any change. I just added some more slides to break things up to maybe make it clearer what I'm presenting. One other little small point. This is a minor point. You notice this slide, the color of this slide is blue. Two kinds of blue, right? Two kinds of blue. When you see Dr. R's slide, they won't be in blue. I think they'll be black and red. Okay. Why is this blue? Anybody know why? In fact, do you know the difference between this blue and this blue? Anybody know? I'm a big basketball fan. I have season tickets to the Hawks. I used to, when I was living in Chapel Hill, I went to all the Tar Heel games. What color is this? Carolina blue. Okay. What color is this? Duke blue. So anyhow, I'm trying to, keep things on an equal par here. But that's why these are blue, just in case you wanted to know. Okay? Aren't you glad you learned that? Okay? Okay? Okay, now let's go to the topic. Okay? And I can tell you what's happened in Carolina basketball history going way back to even 1957. Believe it or not. Somebody's calling me. It's my wife. No, it's not. But I'm going to not answer it. Somebody else. But these things happen. Okay, so what I want to do here is I want to talk about, I'm not going to finish this today, but I want to talk about what is collinearity and what do we mean by multi-collinearity. I want to show you some examples. I want to talk about collinearity in a simple situation where you only have a model with two predictors. And I'm going to talk about collinearity primarily for logistic regression, but I'm even going to consider linear regression because that's where most of the work was done on dealing with linear regression. And then we're going to talk about, well, how do you actually determine whether you have collinearity in your data? How do you diagnose it? And what do you do if you diagnose it? If you find that you have collinearity, what do you do about it? Okay? And so that's what we're going to do. That's what this topic is about. Okay, so this is the first thing. What is collinearity? Okay, this is where I split up a few things. So what I say, collinearity is a regression diagnostics problem. You're trying to figure out in the model that you're working with, you're trying to diagnose whether there's something wrong with the model, whether there's something that's not right about the model. Something's not working. You're not getting good results or reliable results. Okay? So this may happen when you're fitting any kind of mathematical model to a set of data, whether it's logistic regression, linear, or anything that you're going to learn later on in this course or any other course. But more specifically, collinearity occurs is said to be present if one or more of the independent variables, or the predictors, in one's model is highly correlated with other variables, maybe technically a linear function of other variables in the model. Okay. Now, what am I saying? I'm talking about the x's. You're doing logistic regression. You got y, whether it's 0 or 1. If you're talking about binary logistic, if it's ordinal or polynomous, y has 3 values or 5 values, several values. But I'm talking about the x's. And what I'm saying I'm worried about here, or what we're worried about, is when you look at the x's, whether some of the x's are very closely related to some of the other x's. That's what you're worried about, okay? In fact, if for some silly reason you put in age in there twice, and that would really be stupid, right? You somehow, and you forgot that you had and then you put it in again, you know. But if you did that, the model won't run, because you've put 2 variables in the model that are saying the same thing. They're not only are they highly collinear, they're perfectly collinear. They're saying the same thing. The model won't run, okay? And I think I gave you an example of this a couple of weeks ago, or a week or 2 ago, is that what if you've got a variable that you want to put in the model that's got an exposure variable that's got 3 categories? How do you put it in the model? Dummy variables. How many dummy variables? 2. Remember, you're supposed to put 2 dummy variables when you have 3 categories of a variable, of a predictor variable, like the exposure. Okay. What if you put in 3 dummy variables? You know, are you in one or the other, or the other or the other, or the third or the other? What if you put in 3 dummy variables? Well, then the model won't run. And the reason why the model won't run is because once you've put in the 3 variables, any 2 of them is perfectly predictive of the third one. You can come up with an expression, a mathematical statement for getting the third one from the other 2. So the model won't run. That's what's called perfect collinearity. Okay? So that's what you're worried about. Okay? Now, the reason why you're worried about it is because the presence of collinearity can lead to highly unstable estimated regression coefficients. And sometimes, if there is perfect collinearity, like I described, to no solution. The model won't even run if it's perfect collinearity. But it's possible that you have predictors in the model that aren't perfectly correlated, but when you consider any 2 variables or more than 2 variables, 2 of them might closely, if you add them up, they might closely predict the third one, or be very strongly correlated. The sum of 2 might be correlated with a third one, but not perfectly correlated. Well, if that's the case, the model will run, but you might get some weird results. And what the weirdness is, you get highly unstable regression coefficients. What does that mean? Highly unstable regression. You get a beta. We're talking about a beta? And I have to say it's highly unstable. What do we mean about it? What is one way of saying that? One way of saying it is you can't trust the value. I mean, it's just, who knows what it is? You got a number, but it could have been, and the number might have been positive, but maybe it was really negative. That's one way of saying it. But another way of saying unstable, what's another way of saying an estimate's unstable? High variance, right? It's very variable. You know, or the estimate is the variability of the estimate is high. Well, that may happen simply because you have collinearity, not because the actual, if you did the model correctly, you would get you get a high variance. It might not get a high variance if you didn't have collinearity. But it might be unstable, or you get a very high variance or high standard error for an estimate simply because there's and it's sort of misleading you that you've got a variable that the coefficient of a variable that you might think it's not significant when in fact it could be significant. It's just you got a bad model. Okay, so that's the problem here. Okay, now a couple more things. This is where I split some things up. Originally in the thing I had this slide, everything was on the same slide. I was trying to make sure I focused on one step at a time here. So now it may, notice I said, note that collinearity may involve only two highly correlated variables, but that in general, collinearity may involve a relationship among three or more variables. Now think about this. You know, and I think you've seen this, do you know what a correlation matrix is? What's a correlation matrix? It's an array of numbers. A matrix is, there's a mathematical way to talk about it and all that, but just in a simple sense, it's an array of numbers that contains a bunch of correlations. Now, what are we talking about? Well, if you got a bunch of predictors, you also have Y. If you got a bunch of predictors, you can put an output together. You can get there's even a program called PROC-CAR that you might be familiar with in SAS, that you can get a correlation matrix that gives you an estimated correlation of every variable that you're putting in the model with every other variable, pairwise. So you could get pairwise correlations for every variable. And let's say you got 10 variables in your model, you can get every pairwise correlation. That's what I'm saying. Okay? Now, you could look at that correlation matrix, okay? And you look at it and you say, well, some of these correlations between X1 and X4, and we're talking about just two at a time, some of these correlations might be huge. Huge, we're talking about correlation. They can't be more than 1, or they can't be less than -1. But some of them might be 0.999, or some of them between 939, or something like that. That's high. That says that if you see that in a correlation matrix, you got two variables that are almost saying the same thing, right? Isn't that what that says? Okay. So if that happens, you might say, well, I think I should worry about my model, because I got two variables that are saying the same thing, and and if I run the model, I might see the model either doesn't run or it gives me something that I view as unstable. Now, how to do that is something we need to talk about, but there's a problem with that. The problem is that just looking at the correlation matrix by itself, that only deals with pairwise correlations. That only deals with whether one variable is highly correlated with another one. But it doesn't deal with whether, if you're dealing with three variables and you know two of them, that's going to help be very correlated with a third variable. So the correlation matrix is not enough to determine collinearity. The problem may not involve two variables. It may involve three variables or four variables. So that's one issue. How do you figure that out? I'm saying you can't use a correlation. You could. You can always use a correlation matrix as a starting point, but if you see everything looks fine, nothing's that high, you may still have a collinearity problem because it may involve more than two variables. Okay. Now, so that's what I'm saying here. Then I got another statement. Furthermore, collinearity may involve more than one relationship among several variables. You may have 10 variables in your model, 10, X1 through X10. And it may be that when you assess collinearity, or when you look at the relationships, you may find that the variable X1 is very highly correlated with X2. So that's looks like one collinearity problem, but you also may find that X2 is very highly correlated with some linear function, maybe the sum of X3 and X4. So that would mean that you have two problems. You're fitting a model with 10 X's, and you not only have one collinearity or one problem, the relationship, you have two. So how do you figure out how many problems you have? And if you try to figure that out, what do you do about it? Which is one of the things you do. So that's a problem. And that's why we often use the term multi-collinearity instead of just collinearity, because there may be more than one collinearity problem. So then you have sort of multi-collinearity. That's where the word comes in. Okay? So I haven't shown you anything about how to do it. I'm just telling you what it is. Okay, now, another way to view collinearity in terms of the way I described it is, look at this expression. This expression, what is this expression? It's a linear function of the predictors in your model. You notice it doesn't have Y. And I've got P predictors. P might be 10. P might be 3. And it's a linear function. What does this statement say? You read this statement? What's this thing? Is that an equal sign? No, it's a, right? It's an approximately equal sign, okay? So it says this linear function is approximately equal to 0. That's what it says. So that's another way to say what you're talking about when you're talking about collinearity. That somehow the x's, if you put them together in some kind of a form where you've got x1, x2, and you're multiplying by some constant, that's what these a's are, a1, a2, these are constants that you're multiplying by the x's, somehow you can get a linear way of writing the x's, and they're almost, you know, when you put it together, you get approximately 0, okay? Well, that's a way of saying there's a linear dependency among the x's. That's a mathematical way of saying it. Now, of course, there's another way of saying it, is that if this was true, I could solve for x1 in terms of the other x's, right? In other words, if this was true, I can write x1, I could write a formula for it, x1, but of course I'd have to say approximately equal, because it's not equal, and I'd have equal to minus the other x's, a2, x2, and so on, divided by a1. So that would be saying that one predictor is approximately determined by a linear function of the other predictors. So that's sort of the mathematical way of talking about collinearity in terms of linearity. I mean, we can talk about it in general, but if you have this problem, then you got to worry about the fact the model may not be a good model, and you may have a very unreliable model. Now, another thing to notice about this relates to what I wrote in green here. When you look at this expression, and you're thinking about a regression analysis, now you notice that this expression here does not involve y, it only involves the x's. Okay, so if you were thinking of even a linear regression analysis, because the outcome doesn't involve a 0-1 outcome, maybe all these x's are continuous. Well, if they're all binary, then it's a little bit more common. But let's say they're all continuous, okay? And you got one x written as a sort of a function of the other x's. And in a way, it's a linear function, because if I divide a2 by a1 and for each one of these coefficients, I just get a linear expression here. Okay, what do you think about? What about a model here? What kind of a model might you fit? You might fit a model that tries to predict x1 from the other predictors, right? Right? That's what you could do. Okay. Now, if you do that, and you fit that model, and it turns out the other x's very strongly taken together predict x1, what might you, when you learned your linear regression course, when you took the linear regression course last semester, what would that translate to in terms of a linear regression term? I've used the word R square down here. You remember R square? If you've got a model where the predictors are almost perfectly predicting the outcome, in this case the outcome's x1, okay, then you're talking about an R square, which is a measure of how strong the x's predict y, is an R square close to 1. That's what you're talking about. So that's another way to view what collinearity is about. If you talk about looking at any one variable as a function or related to any of the other variables together, then maybe you might expect R squares, when you're looking at one variable and the other ones, to be close to 1. And that involves a lot of R squares, x1 versus x2 and the others, x2 versus the others. It might involve 10 R squares if you've got 10 x's, okay? Each one versus the other ones, okay? So R square is something that people have often thought about as a way to address collinearity, because now you're dealing with several variables, but there's a problem with that. So I'm just sort of not there yet to talk about all this, but okay, so examples of collinearity. I'm going to get there, okay? Examples of collinearity. Well, one example is you got two variables in the model that are very highly correlated. That's a problem. And if they are, you might find that the model doesn't run very well, or it doesn't run at all. You might have a situation where, just like I said, x3, a third variable, is highly correlated between the difference in two other variables. That could cause a problem where the model may not run or not run well. Another problem is when you have product terms in the model, right? Whenever you have a product term in the model, that's a product of two terms that went together to make the product. So it may be the product is highly correlated with one of the components of the product, or both of them, okay? Maybe and maybe not. And then, of course, you could have a model sometimes called a polynomial model, where you have a variable and then you have the square of the variable. You have age and age squared. Or you have age, a squared, and age cubed. Well, x squared comes from x, so maybe there would be some correlation there, and maybe that would cause a problem. Maybe it would, maybe it wouldn't, okay? So these are all examples, okay? So what I'm saying, it's not, one of the messages is you don't want to just consider pairwise, as I've done either in some of these examples, okay? Now here's another example. Two variables may not be inherently collinear, yet they may turn out to be collinear in the data. What do I mean by that? Well, I mean, gender and race, you know, they're different variables. They're measuring different things, I think, right? Okay, but it may turn out that, I mean, this would be sort of stupid to do, but it may turn out you had a data set, it only had 5 people in the data set, and this is what the data looked like. And it turns out that, you know, that only you either have only black females or white males. If that's what the data showed, you'd have collinearity in the data. You have perfect collinearity. That model wouldn't run. Okay? Well, the best way to correct for that is don't do that study, you know, I guess. Or make sure you got enough data so if you're dealing with variables that you know are very, you know, they're not related to one or inherently related, take enough data so you don't get that. But that's, you know, so that's, you know, and it could even be that even if you have, it may turn out they're not inherently collinear, and just the way you collected them, this is just sort of like the same, just a different example, could be that when you looked at these 5 subjects, turns out they were collinear, but that doesn't mean you would get that if you looked at a lot more. Okay, that's all I'm saying. You could get collinear results, but if you do a study well and you ignore that, you still could have collinearity. Okay, now, here's the next thing I want to show you. Okay, what have I put here? What's up here? There's a model here. What kind of a model is that? Is it a logistic regression model? No, it's a linear regression model, okay? Y is the outcome, okay? And it's got 2 predictors, okay? Now, you may have learned this last semester, but you can show, if you do a little math, is that when you fit this model to get estimates of beta naught, beta 1, and beta 2, beta 1 hat, beta 2 hat, and all that, one could show mathematically that the estimated variance, which measures precision or stability of the estimate, the estimated variance can be written of beta 1 hat is some constant times the formula 1 over 1 minus r squared, which is the square of the correlation between x1 and x2. And you can also show that the variance, the estimated variance of beta 2 hat is a different constant times 1 over 1 minus r squared x1, the correlation between x1 and x2. So what is this saying? Well, think about it, is that if this correlation was exactly 1, and it's in both these formulas, this correlation was exactly 1. If x1 and x2 were perfectly correlated, what happens to the variance? It's infinite. It blows up. What does that mean about stability of your estimate? It's terrible. It's the worst you can get. You don't have a good estimate. It blows up. Okay? If it turns out these 2 estimates were approximately 1, but not equal to 1, but they were close to 1, then what you're going to get when you go, whatever this constant is, 1 over 1 minus r squared, if this is close to 1, this is 1 over something close to 0, but not exactly 0, that's going to be high. So you're going to get a high variance for both of these estimates. And that means if you have this high correlation between, and you only have 2 variables in the model, you got a collinearity problem. What we're saying, you have something, you got a model that's unstable. Well, this made someone who wrote a couple people that wrote a book, 3 people, and they basically said, well, maybe what you should do when you're dealing with collinearity, one way to measure it is to look at this thing which is characteristic of both of these 2 estimates of the main ones of interest, because that's the constant, why don't you just look at this thing and say, well, maybe that's how I'm going to diagnose collinearity. I'm going to look at this 1 over 1 minus r squared and see whether it's high or not. Okay? But you notice this r squared, if there's only 2 x's in the model, that r squared, that square of the correlation between, that's actually the capital R square for a model with only 2 things. Remember, R square, we talked about R square when you got several x's. This is what happens when you try to predict one of them from all the others. If you only have 2 of them, this is a simple version of this. So this came up and said, well, this might be a good way to measure or diagnose collinearity, compute this thing. Well, this is fine if you have 2 variables. What if you have several of them? Well, that goes back to what I originally was saying. What about using r squared to do this? Okay. So what about saying using 1 over 1 minus r squared I as some way to diagnose collinearity? That's what this is saying. That's what this is suggesting. Okay. And you notice this says VIF stands for variance inflation factor. That's a measure that if it's high, it suggests the variance is inflated. And if it's infinite, it's so inflated that you've got nothing. You don't have a good model. Okay. Now, what do I mean by VFI? What do I mean by that? What's the I referred to? Well, you got 10 x's. I is any one of them. So what you're going to compute is the variance inflation factor, or the r square for each of 1x related to all the others. That's what you're going to do. And you're going to get, if there are 10 x's, you're going to get 10 of these, 10 VIFs, okay? And then you're going to look at them and decide whether you think some of them are high, okay? And of course, one of the big questions there is, how high is high? And that's a big question in this whole collinearity. How high is high, okay? Okay, so, well, it turns out that when you've got a multiple regression model, you can show that the variance of any estimated regression coefficient is a constant times the VIF that relates that variable with the other ones. And it also turns out, we know that if you can perfectly predict x sub I from the other x's, then r sub I squared is 1. So this thing is going to be infinity, right? Okay. Now, there's a rough rule that people have come up with. Again, how high is high? This is a rough rule. Rough. Okay? Okay? It says if the VIF is greater than 10, that suggests collinearity. It's a rough rule. Okay? Now, what makes sense about that? Well, it does make sense. It's not that rough, but it basically says, well, if the VIF is greater than 10, then the r squared, 1 minus r squared, okay, the r squared has to be greater than 0.90. Just a little algebra, the r squared has to be greater than, and so the r, I didn't separate some of these terms, the words in there, but the r has to be greater than 0.95. So if you've got a VIF that's greater than 10, that suggests that this one variable is being strongly predicted by the other variables. That's a way of coming up with why 10. Now, if it was 20, it would be even more, if the VIF had to be greater than 20, that would require something worse or more stringent than 20 is more stringent than 10. Okay. So, but now, look at this. Look at this table now that I've just done. Okay. What have I done here? I've used this example. I got 10 x's. Suppose you're fitting a logistic model or a linear model. It has 10 x's. And suppose when you do that, you get these 10 VIFs. Okay. Now you notice that I got ... because I didn't want to show you all 10. I just wanted to show you some of them just to give you an idea of what's going on here or what you might do. What do you notice? 2 of them are circled. Why? Because they're greater than 10, right? The other 2 that I've listed there aren't circled because they're less than 10. So if you saw this, what would you be tempted to say about possible collinearity? That there is a collinearity problem that involves x2 and x10, right? That's what you'd say, using VIFs. Okay? So that's one way you could diagnose collinearity. Okay? Using VIFs, you know, if you got something like this, and then you could look at the correlation itself, and you could see, and you could look at the fitted model and see if it fits or how reliable it is. But what if you got this? What if you got this? What would this say? Now I got 3 of them that are greater than 10. Okay, does that say there's one collinearity problem involving these 3? Or could it be 2 collinearity problems involving X2 with X6 and X2 with X10 or anything? I'm not sure what it might be. See, problem with using VIFs to diagnose collinearity is that it doesn't, you know, it says not clear if there is one collinearity problem or 2 collinearity problems. It's not clear how many collinearity problems there are and which variables are involved with which problem. You can't tell from this. And that's why people like to use VIFs, but it doesn't solve the problem. It's not the best way to do it, and so somebody came up with another way to do this. Okay? Another way to do this. Okay? Even though it's some way that you can see that it sort of makes sense, but if you got something like this, it's not that easy. Okay, so the other way to do it is to use what are called condition indices that came out of a book by these 3 people, Belsey, Koo, and Welsh, book that they spent I don't know how many years writing, regression diagnostics, and primarily this whole book dealt with linear regression. And when are you going to wind up having a problem where the model doesn't fit well because of collinearity? Or what is collinearity? They wrote another book a number of years later, in 1991, where they dealt with a little bit more and they went into some other models, like logistic regression models, but they didn't go into it that. So basically what they said was using something called a condition index and something else called VDPs. VDPs, and this is your name dropping, how's your VDP today? Oh, I don't know. VDP stands for variance, I forgot. Variance decomposition proportion. Variance decomposition proportion. That's how you diagnose collinearity. And that's what's built into SAS Proc Reg. Proc Reg has a procedure, and it's an option. It's called the colin option. And if you use the colin option, it'll give you this information. Okay? Now, I want to show you, before the end of the class today, how it works. But I'm not going to define these. There's too many words here. So I want to show you how much it works by showing you this table. Skip to this table. Okay? Is it okay? I skipped. You don't want to see those other ones. Well, you might want to go back to them. Okay? But this table explains how it works. It doesn't explain why it works. It doesn't explain the theory. And the theory about this is a little complicated, and it was in the middle of the PowerPoint presentation, and I put it at the end, because whether you really want to know the theory or not, most of you don't care. They want to know what to do and what it is and all that, so I put it at the end. Okay, so here's what it is. Now, look at what's on this thing. Can you figure out from these information, don't just look at the numbers or the letters here, and don't look what's at the bottom. There's a model being fit. Could you figure out what the model was? Do you have any idea from what you see here what's involved in the model? Up in the top, you see EC1, C2, C3, EC1, EC, just like what I talked about when I was talking about polynomous and order. But this is it's either a linear or logistic model, and these are the variables in the model, and there's an intercept. Okay? So let's say you were fitting this model. And let's say it was a linear regression model because you're going to, that's the way it works the best as far as Reg is concerned. Let's say you fit this model, and then you crank, there's a program, in SAS, it's the colin option. If you ran the colin option, you'd get this kind of output. And what you'd get is, now, how many parameters are here? Parameters. Well, there's 7 betas and a beta 0, so there's 8 parameters, right? How many values do you have in the first column? How many values do you have? 8. So you will have as many numbers here as you have parameters in your model. That's the way it works. Okay. Now, these numbers start at 1 and they go up. And these numbers are called condition indices, whatever they are, whatever they mean, whatever the theory behind it. But these are not, and the way they work is the higher they are, the more likely you have collinearity. That's the way it works. If they're high, that suggests, more likely suggests collinearity than if they're low. And the lowest it could ever be, given the way they're defined, the lowest value is 1 and can go up as high as possible. Now you notice that I've got 2 of these CI. CI doesn't stand for confidence interval, it stands for condition index. Okay? And you notice the 2 highest ones are in bold, and they're not the same. One is a lot higher than the other, but I've put them in bold because somebody would look at these and say, well, I think these are high, and these other ones aren't high. Now, where that came from was when these guys, these 3 guys, actually, when they wrote this book, they did a whole bunch of work to decide how high is high when you're looking at collinearity for linear regression. And they came up with a rough rule that says that if the condition index is at least 30 or around 30, that's high. Just like, remember I came up with the rule, I didn't, the rule of the VIF greater than 10? They came up with the rule of 30. Now, it's not a rule, it's a guide, okay? And that should worry you because, well, what if it's 28? What if it's 32? And stuff like that, okay? But you notice the highest one is 99.8. That's a lot higher than 30, okay? And this is 30.8, it's close to the thing. Now, so what happens is the first thing you do when you look at this kind of output is you go down this thing and you say, well, are there any high condition indices? And what you do is you look at the things you try to put in bold, or you try to identify those that are high, at least 30. And one of them is a lot higher, okay? And then what you would say is it looks like there's the potential for 2 collinearity problems, because 2 of them are at least 30. That's the way you'd start with this thing. That doesn't have you finish it. It's not finished yet, okay? That's the way you start. Then the next thing you do is you say, okay, let's look at the worst one, the highest one, the 99.8, okay? What do I do next? 99.8, and I'm getting close to the time we're going to quit, but 99.8, I want to do this. You look over here and you notice that there are a bunch of numbers here, and you notice that 3 of the numbers are in bold, and the other ones aren't. On this last row, okay? Why have I put these 3 in bold? Because they're the 3 highest, right? Okay, so again, there is an issue of how high is high, right? That's an issue with this whole thing, okay? So you might say, I don't like this, how high is high, but these people, I don't know, they spent half their life, I don't know how much they spent on trying to figure this thing out. And they said, if these numbers, now these numbers are called VDPs, variance decomposition proportions. That's what these numbers are. And you're going to get this for every condition index, you're going to get a row of variance decomposition proportions. Now, by the way, just to explain what that is, I have some words, but look at any column here. Look at any column here. Look at the E column. Suppose I add up all the numbers in the E column. What do I get? 1. What if I do the next column? Any other column? Okay, so what I'm doing is, for any variable, I'm dividing up something into proportions that add up to 1. That's what these are doing, okay? And what I'm essentially doing is, that's what they describe, is I'm taking the variability according to this variable and dividing it up into how much proportion each one of these condition indices contributes to the variability of this variable. And you notice these 2 are high. Okay. Now, how high is high? They came up with a rough rule of 0.5. Rough rule. So I put in bold 0.430, 0.700, and 0.930. This isn't even 0.5, but it's close. Okay. Now, the way you would proceed with this, and I'm just sort of giving you the idea of what you do, the way you proceed with this, you say, okay, this is the highest condition index, and it's very high. And it looks like that there were 3 bold VDPs, 3 high VDPs. What I'm then going to do is going to go to the top of the table, and what do I find? E, C3, and what? EC3, right? And what I'm going to say is, based on the way I've just done this, I'm going to determine that if there's any collinearity problem, it involves these three variables, E, C3, and EC3. That's how you do it, okay? That's how you do it for the first one, okay? And the way you do it, the way it's generally done, the way it's recommended that you do it for the first one. And then you, based on what you decide on the first one, you do something about it. And then you see if you have another problem. You don't do it for the first one and the second one. You do it one at a time, one collinearity problem at a time. Now, if I had, based on this thing, determined that there was a collinearity problem, and it involved EC3 and EC3, and I had to do something about it in order to make my model stable, what would I do? What would I do? I drop something, because these three variables can't be in the model. They're somehow conjoined to give you an unstable model. And I wouldn't drop any other because I've decided these are the three variables that are involved. What would I do? Would I drop E? Why not? And the model's not hierarchically well formulated. Would I drop C3? The only one I could drop is EC3. That's what I would drop. That's how it proceeds. I would drop EC3, and then what I do is I'd say, okay, that's out of the model, okay, because of this thing that I've seen. And then I'd refit the model without EC3. And then what I would get is I would have only 7 condition indices. I wouldn't have 8 because I've dropped one of these predictor variables, okay? And then when I look at the 7, would I get a 30.8 for the highest condition index when there's 7 left? Not necessarily. It may turn out, once I got rid of EC3, I dealt with the whole problem. And I fit what's left, then the highest thing is much less than 30, maybe less than 20. So that's why you do this sequentially. I'm just describing a process to do it. You do it sequentially. First thing you do, you take care of the highest one, and you do something about it if you decide there's collinearity, and then you go again, you refit the model, and you keep doing it, okay? Until you don't find any collinearity. That's how you do it. Okay? So you got that? That's the main thing. And it's not that bad. But there are always if, ands, or buts. And one of the if, ands, or buts is how high is high. Okay? And how high is high in terms of the VDPs, and how high is high in terms of the condition indices. But there are other buts. But here's the last thing I do before we quit, is I want to show you another table. Actually, I want to show you another slide. Look at this slide. Look at this slide and compare it to this slide. Here's a slide. This is like an eye test, and I'm about to get one. You know, this is an eye test. Here's one slide, and here's another slide. What's the difference between these two slides? It's just mirror image, right? Okay. So the output could look like this, or the output could look like this, depending upon what the computer program is that you're using, okay? So depending on which computer program you're using, you can get one or the other. Well, it turns out if you're doing linear regression and you're using the colin option, then this is the way it looks. If you're doing logistic regression and you can't use the colin option because it's not in there. Doesn't have it. Proc Logistic doesn't have it. In fact, there's something called a macro that was developed by somebody at CDC about 20 years ago, and a lot of our PhD students over the years modified that macro and made it adjust, made it fit, made it work with a lot of different models, not only logistic, but Cox regression, Poisson regression, a whole bunch of other things. Okay? And if you're using this macro, that's the way it's going to look. It's going to look like this. Okay? Well, it's the same thing. You just have the highest thing is up here. You just have to remember how to do it. Okay? So that's most of what you need to know. But what I need to do next time is show you something about the computer, how the computer works. You know, how you do this on the computer. And what the output looks like. Okay? That's the main thing. And I'm not going to do much of the theory here, but that's what we're going to do. Today is Tuesday, so that's what we're going to do on Thursday. Okay? Even though this topic isn't covered on the exam, It's something you ought to know about, because what you're worried about when you're doing analysis is maybe you got a model that's not working, okay? So, see you Thursday. Oh, today's Thursday. See you Tuesday. I got it all wrong. See you Tuesday, right. Tuesday, right. Thank you, John. Thank you so much. Thank you. Tuesday. Oh.